Okay. Well, thanks for coming today. We'll go ahead and get started. Just a note to begin with, we are recording this, just so you're aware, and live streaming it. So any comments that you have, questions, anything like that, feel free to raise them, but they are being recorded. So yeah, I'm excited to take some time today and talk about managing research software projects. I'm Daniel. I am a new postdoc in Titus's lab a few months ago. My research interests are in genome informatics, in particular genome organization, genome composition, and structural variation in eukaryotic genomes. But throughout my training, I've had quite a bit of experience with research software, something I enjoy, something I'm passionate about. I learned computer programming first as an undergrad, and then during my graduate training had a chance to apply that to some problems, at least that I felt really cool, very interesting problems in genome biology. And by the way, I'm sorry, we don't know what's happening with the projector, so hopefully that'll sort itself out or not, but so sorry about that. And then, yeah, I'm also involved with the Software Carpentry Foundation, which provides training in basic lab skills, basic computational or scientific computing skills for scientists. So those are some of the experiences that I'll bring to bear on today's discussion. I first want to say thanks to several people without whose help I wouldn't be here today. Sasha Steinbus and Gordon Grema are graduates of the research group of Stefan Kurz, Hamburg, Germany. And when I was a very early graduate student, I got involved in using their software called Genome Tools, and they gave me a very good example of how to develop software in an open community, and how to basically treat your colleagues well. They gave me a very good example of a lot of what I do now with my own research projects. My advisor, yeah, this is pretty bad. My advisor, Titus Brown, who's a very good mentor in a lot of ways, but also has a very good open research science project that I am now contributing to along with my colleagues in the lab. And then Greg Wilson, the founder of the Software Carpentry Foundation, has contributed a lot to early drafts of the material that we'll be discussing today. Okay, so why are we here? What's motivating this talk? For better and for worse, a lot of scientific disciplines are becoming increasingly data intensive, and as a result, we're depending a whole lot more on software for analysis, for modeling, simulation, and lots of things. This is great in a lot of ways, but one of the big challenges that we have is that most scientists have little or no formal training in software development, computer programming. And so this creates a problem. If you know, most labs can't afford to employ full-time programmers, and so it's up to the scientists to learn how to do the programming, learn how to create and use the software that they need for their research. So let's take a second. By show of hands, how many of you use software that has been written by others in your research? I think everybody. Almost everybody. How many of you use software that you've written for your research? Okay, so several, a lot fewer. How many of you I guess, have formal training in computer programming, have taken classes? Okay, so 2, 3 hands. How many of you have any kind of formal training in software engineering and kind of the process of building and architecting software? Okay, I think we're down to 1. So software is, I mean, the code is a very important part of the software, but a research software project is more than just the source code. There's how the source code is organized and how other ancillary products are organized with it, such as documentation, supporting data, and other things. It's also communication. How do we work on our software? How do we share it with others? How do we use it? And how do we disseminate the findings of our research software projects? And then it's the process of interacting with others in creating the software. So you don't have to be a professional software developer to have a successful research software project. But learning some of the tricks of the trade that software engineers use can make a big impact on the quality and the success of your research software project. So that's what we're going to discuss today. So kind of a really rough overview of what we're going to discuss. We're going to talk about some key salient features of research software projects, kind of what our end goal is, some basics of project organization and how to make software actually usable by others or by yourself in 6 months when you have revisions on your paper and have to actually update your code that you haven't touched for 6 months. Some critical fixtures, automated testing and version control, and how to use these for your research software project. And then, okay, process and strategies. How do we make all these ideals happen practically? The scope of the projects that we're discussing are small collaborative research projects. We're talking on the scale of 2, 3, 4 people for time scales of 3 to 6 months, maybe a little bit longer, but anytime that you start getting more people involved or longer time scales, a lot of the strategies that we discussed today are going to need, I mean, you're going to need additional planning and additional strategies that we're not going to discuss today. But in my experience, a lot of the software projects that we have are on this scale. Projects where the contributors are scientists that are frequently time slicing with other projects. So this research software project might not be the only thing that you're working on. You might be collaborating with other scientists. You might have several projects that you're trying to juggle. So it's not something that you're devoting your full attention to. And then kind of the everybody makes coffee approach, where you don't have a whole lot of specialization. Everybody essentially helps out with everything in the code base. So, you know, again, a lot of the things that we discussed today are going to be general, but these are the kind of assumptions that we make about what type of projects we're discussing.
I just asked somebody from my team to take a look at
Okay.
what's going on. 30 seconds into it, I can't get it to counties.
Okay.
Yeah.
Sounds good.
She's going BGA. Doing that over VGA. Have you tried just reconnecting the dongle at all?
Yeah.
This,
Yeah.
you tried that.
Yeah. Tried HDMI as well, a different dongle. I mean, it very well might be there. So.
Okay. So you tried that. That's
Yeah.
the same blinking result. Yeah, it's gonna he'd be there either the computer or the projector. So just does it like every 20 seconds or 10 seconds.
Well, ever since you gave it a good shove, I don't think it's been, it might have just been a connection.
Would you push in something down below, or?
No, there it goes again, huh? I think it's probably, I think it's the VGA cable. What's this? Yeah, it's the cable. I can try getting a different cable.
We have HDMI. I mean, we can.
But what, was there that were VGA?
Yeah, it was doing HDMI.
Unless it's this, then, right?
Yeah, I think it might be the connection.
Do you have it on, on the internet? The presentation? Want to just try mine?
Yeah.
That'd be a good idea.
On. Screen sharing on. Hide. And did you send it to me before?
No.
Okay.
Okay. I'll just put it on the server.
Demo effect on a presentation scale. It hasn't.
No, it hasn't blinked since.
Okay, so it's your laptop.
It's his USB-C connection. Bummer.
Oh, well, it's new and it's on warranty.
Yeah, this is a.
Right, what is it? It's a PowerPoint?
Yeah.
Okay. Any second now. No. Hello. Hello. Here we are.
Taking notes, there's going to be a quiz on this.
Well, we'll just wait. All right, go fun.
Go see.
Thanks. Right. You're now resuming the talk. Right, just a slight technical difficulty.
Okay, one second.
So is it showing the slides on the stream or the presenter view? Okay, good. Okay. Okay, so I think this is where we left off. Okay, so what distinguishes research software projects from other software projects? Developers in a research software project are going to typically have some pretty extensive knowledge of the scientific domain that they're studying, but as we demonstrated a few minutes ago, typically self-taught programmers. In terms of the questions that you're studying, you may not know they might not know all the right answers, but you do know some. And then the requirements of the software are typically kind of refined as the software is developed. It's not like, in some cases you might have a project where it's a very clearly defined, this is what we have to produce, this is what the input's going to look like, this is what the output should be, in which case it's more of kind of an engineering challenge. But a lot of times it's more of a kind of an exploration. Like, okay, what does the data look like? What do we need to be doing? And you figure a lot of that out along the way. Scientific problems that we use the research software to bear are often subtle as well as complex. And getting funding and for research software can be a challenge. I guess the economy of academics is publishable papers, and so software you can write up a paper about a piece of software, but software itself is something that is still not valued as much as a primary research output. And then, of course, getting credit for the software can be challenging as well. So these are some of the considerations, some of the key features of the types of projects that we work on. What is the end goal? In a lot of ways, software projects aren't ever really done or complete, but some main goals that we want to accomplish is that we want software that can be used by others. Even if you are not interested or don't expect colleagues from other institutions or other places in your institution to use your software, there's always colleagues within your lab or friends. And yourself in 6 months, the things that you need to do to make your software usable for yourself are things that will make software easier for others to use. You want software that you're reasonably confident that the results are correct. You want software where small changes, extensions, new features can be added safely and easily without breaking everything. And then you want software that's fast enough that it's actually useful. How fast that is kind of might depend on your field of interest. A lot of experimental scientists are used to incubating samples in the lab for hours on end, and so running a script for half an hour, that's a very inefficient script that takes 30 minutes to run might not be a big deal. Whereas for somebody that needs to apply a program to 100,000 different samples, there might be some performance considerations there. So, and whatever your problem is, the software needs to be fast enough to be useful for what you're studying. So, some very basic things that can help us accomplish these goals is some basic organizational strategies. Bill Noble, several years ago, published a paper on suggestions for how to organize a research software project. This diagram kind of shows a rough idea of how he's organized it. A main top-level directory that's labeled according to the project, and then subdirectories for different files, different components of the research software project. Specifically, he suggests that put text documents such as a manuscript for the analysis or technical documentation in a doc directory, any raw data or metadata associated with the project in a data directory, files generated from the raw data in a results directory, along with a lab notebook describing how the results were generated, which commands were run, what commands worked, what commands didn't work, source SRC directory for source code, and then compiled programs or external third-party scripts in a bin directory. And then the basic idea is to name all the files, to name all the directories, and all the different components of the project according to their contents or the role that they play. You know, the actual specifics of what you use, you know, I don't think the details here are really important, but I think the principles are. I mean, if you decide to call your source directory code, or, you know, you can adapt details as you want. But the idea is that if you name the files in your project according to their content, instead of just, you know, doit.sh or analysis.r, you know, actually try to give some context and some to the files. That being said, there is some value in following common conventions, and the conventions that we discussed earlier here with source and bin and doc, these are conventions that people use frequently. And so that if you do follow these types of conventions, you can kind of reduce the amount of thinking that somebody has to do about things that, you know, aren't really important. You can kind of signal what your intent is by naming things a certain way. And then, in addition to organizing the files in the directory in your projects, there's a few other suggestions from a paper by Morgan Tashik about ways that you can make your research more usable by others or more usable by yourself in different environments. First is to have a descriptive README file that provides a basic synopsis of the project, what it's about, and then any dependencies that might need to be installed for you to run the project. So when you execute the code on the command line, it's always very helpful to provide a usage statement that says, okay, if you want to run this software, these are the settings that you can configure. When we use a graphical interface like Mac or Windows, we have menus at the top, and we can kind of get an idea of what the software can do by browsing through the menus. Like, okay, it can import, it can export, I can change this setting, I can change that setting. Well, when you develop research software, you need some way of conveying that same type of information to your users, and so providing a usage statement of what settings are there and how you can adjust them is helpful. Assigning meaningful version numbers to the software is very important. And then the next point along with that, making older versions of your software available. As you adapt and improve your software over time, you know, if you run an analysis and then over the next 3 months make some changes and then go back and rerun the analysis and you're not able to reproduce your previous results, that can be a big problem. It can be very frustrating, and taking periodic checkpoints of your code and your project, and, you know, assigning that this version numbers is something, and then storing those somewhere, saving them and not touching them. That is something that can be a big help for you to be able to retrace your steps, and to be able to reproduce previous results that you've done. There are conventions for doing this. If you're interested in how to apply this in a project, you might look up something called semantic versioning. That's used by a lot of projects, but really, as long as you're mindful of this approach and using it, it can be helpful. It's always a good idea if software exists to do some of the things that you need to do, rather than reinventing the wheel and writing things from scratch. As much as you can reasonably do, using this other software and bringing it in can be a big help. some things that might seem easy to implement yourself, once you start getting into the nitty-gritty, you can see that, okay, well, actually, there's a lot of things to consider. You might introduce bugs that other software has already dealt with, and as much as reasonable, it's a good idea to reuse software. You also don't want to require users to have special privileges to install or run software on a particular system. This is particularly a challenge if you need a lot of memory or a lot of runtime for a job and you have to connect to a cluster or some kind of shared computing environment. If you have to have root privileges, well then I'm going to guess that 90% of your users are just not even going to be able to install it or use it. So along with being able to configure settings on the command line, you want to eliminate hard-coded paths in your code. And so if you have a file on your computer and that file is always in the same place every time that you need to use it, it's very tempting to just say, okay, look in users, Daniel, data, myreads.txt, and just assume that that's always going to be there. Well, as soon as you need to run your software on another computer, or as soon as your colleague needs to run that software, that file, I can guarantee you, is not going to be in the same place. So if you have that file path hard-coded, it's going to be problematic. So provide ways for you and others to specify the location of the data files rather than hard-coding them. Enable command line configuration with any settings, any interesting parameters, anything that can change the behavior of your software. You want to be able to configure that from the command line rather than having to go and edit the source code of your script and say, okay, change the frequency from 2 to 4, or change the error rate from 0.5 to 0.1. You don't want to be doing that. You want to be able to change that behavior on the command line. It's always useful to provide a small data set to confirm that the software is installed correctly. So if you need to run this on another computer, or if your colleague needs to run it, you need to be able to provide something where they can, okay, run these 3 steps, and this is the output you should get. And if you get that output, then everything's good. If not, if you don't get that output, then don't try to run this on your data, because it's not, you're not going to get good results. And then finally, you want software that's going to produce identical results when given identical inputs. If you run the same command on the same data multiple times, you get different results. That's almost guaranteed to be a bug or a problem with your code. I guess in some cases, if you have a randomized algorithm, that might give you slightly different results, although they should be very similar. And if that's the case, then you might want to look into allowing users to provide a random seed so that they can control the behavior of the randomized algorithm and get the same exact output when you run the same command multiple times. So, again, the whole idea of these types of usability and robustness guidelines is so that you can take something that only works on your laptop and that's it, to something that you can move to other computers, you can send to your friends, your colleagues, and they're able to use that software elsewhere. You may not expect or even want to engage the wider community in your software project. However, funding agencies and journals are becoming more serious about requiring source code to be published when papers are published. And so whatever your feelings on it are, your source code for your research project is actually going to be out there. There's good arguments for developing in the open. I'm not going to get into that today. But one of the things that you need to consider is how do you want people to use your software? By default, if you don't specify any licensing information, your research software falls under copyright, and you have
I mean, basically nobody has any rights to do anything with your software. And so there are a variety of licenses that you can choose to include with your software. You can specify that anyone can use the software for anything really, commercial or non-commercial. MIT and BSD style licenses are probably what you want there. Or you can require people that if they change or redistribute your software that they have to follow your licensing, in which case you'll choose something like the GPL license. But just something that you'll need to think about when your software is published. And again, on getting credit for software, software is a research product. If others use your software, you should want and expect them to cite you for that. You can get a digital object identifier if you. There's a variety of services that will provide this. Zenodo is one of them, and you can include, along with your software, a little note that says, "Hey, if you use this, please cite us," and basically provide some instructions on how to do that. If you are interested in contributions to your software, include a note on your process. How are contributions received? How are they handled and stuff like that? And then also a code of conduct specifying the social rules of your project can be helpful. So just a quick story about community engagement. I was working on a personal research software project, and I hadn't really engaged anybody in it. It's not that I didn't want people to contribute, but I definitely didn't expect anything. I got emails every once in a while from people saying, "Hey, can you help me install this?" But I wasn't sure how serious anybody was using this. One day out of the blue, I got this bug report from this developer that said, "Hey, I can't install your software if I don't have Git installed on my system." And he reported this bug, and then like 3 minutes later, he sent me a patch. Said, "Hey, here's a fix for that. If you want to fix your code, you can just integrate this fix." And so, I mean, I hadn't solicited any feedback. I didn't know this was a problem, but because I had put my source code out there, because I had licensed it, somebody was interested in using it, and they were interested enough that they wanted to fix it so that it was easier for them to use. So that's something you might consider about community engagement. So those are some of the basics of what you want in a project. If your project is organized, you've taken some steps to make it usable and runnable in a variety of environments. You've licensed it and added some citation info. What's next? I want to argue that there are two really critical components that you're going to want to have a part of any research software project. The first is automated testing. So at an early stage in developing the code, you're going to want to have some type of correctness test. You want to have some way of evaluating whether your software is doing what you're expecting it to do. So if you don't already have that in your research project, you definitely need that. Otherwise, you are guaranteed to have bugs and problems in your code. And so once you have these tests of correctness in place, with a little bit of time investment, you can automate these so that you don't have to manually, hand by hand, execute the commands to do those tests. You have one little kind of button push that runs everything for you, evaluates and makes sure that everything is on the up and up. So if you do that, then this allows you to execute these tests automatically and frequently, so that any time that you want to make a change to the code, add new features, fix bugs, clean up the code, anytime you do that, this ensures that changes that you make to the code don't break what's already working. So automated testing is very important. There's a variety of different types of tests that you can do. Smoke tests or sanity checks are literally like, hey, when I invoke this code, nothing blows up. So I mean, that's kind of a really basic test of, you know, can I run this code and can I produce something that doesn't look like complete garbage or that doesn't, you know, bring my system down. Just some really basic sanity checks. If you have your code organized into functions or submodules, then there are things called unit tests that can allow you to test the behavior of really small units of your code. And these are typically aimed at giving the developers confidence that they can use these functions in various places and that those functions are going to behave properly. Functional tests are on larger units of code, typically entire modules or scripts, programs. And these are typically aimed at users so that users can confidently, you know, if I execute program A, it's going to give me the output that I expect it to. And then another type of test, often referred to regression tests, which essentially whenever a bug is reported and then fixed, a common approach is to write a new test right then to assure that a test specific for that bug to make sure that that bug doesn't crop up again. So if you want to integrate more automated testing into your project, one question is how do you know what test to write? One thing that you can do is you can measure the code coverage that your tests provide. Most programming languages have testing platforms that, you know, you specify your tests, and then as you execute your tests, these platforms will identify the lines of code that are executed during those tests. So if you have 3 scripts that you're testing, and then, you know, you execute your automated tests, and one of the scripts, like, you know, line 50 to line 100, is never executed when you're running those tests, well, then it'll tell that to you. It'll say, hey, these lines are never executed, so they could be completely wrong, and you would never know. And so it'll report. It'll say, okay, you have 80% test coverage, 85% test coverage, and it'll say, hey, you need to write some tests that execute these lines of code. Another approach is to write, you know, as I mentioned, write regression tests for bugs. If you find a bug or if somebody else reports a bug and you fix it, then right then is a really good time to write a new test to make sure that that bug doesn't happen again. And then something we'll discuss a little bit more later is called test-driven development. It's a strategy where some people, you know, the idea is to write a test for a certain behavior that if you're going to implement a function or implement some type of feature, you design that beforehand and say, okay, this is what my input is, this is what my output's going to be. I'm going to write the test for that function before I even write the function. So we'll discuss that a little bit more later. So yeah, automated testing is one thing that is critical for your research software project. Next thing, take a second. Does this look familiar to anybody? You might have seen this before. You know, data files, tests, retests. Use this one. No, really, use this one. Okay, starting over. You know, I've seen this more with manuscripts than with data files, but, you know, the idea is pretty similar. How do we organize all this? So I want to take a few minutes. I want you guys to chat with the person next to you. Think about what your best and your worst stories of project organization are. These can be either coding, you know, software projects, or it can be manuscripts. This can be personal or preferably collaborative. And so think about it and then consider, and discuss with your neighbor, what for the really bad experience, what didn't work? What was frustrating? And then for the good experience, what worked well? So take a few minutes, let's discuss this, and then we'll kind of come together in a few minutes to see what everyone has to say.
This is becoming someone tells me, oh, you should look at that article. What's it called? Oh, observations and that's about it. Another student, and she told me, I listened to papers. She was paper on that. So I did my account, and then I had 21 papers. Recommendations. To me, it's $5 a month, and it's a problem. It's a whole separate problem. I don't like getting work in progress. I want to see what I'm assuming that I move over.
Okay, let's come back together. Yeah. So who thinks they have the best, worst, like, horror story of a collaboration project that they want to share with everybody? Anyone interested in talking about a bad experience they had? I have one, but I would be more interested to hear what you guys have to say. Yes, thanks.
So I was working on a grant proposal that was due way too soon with a fairly large group of people. And so I don't know who decided on this, but we all kind of had our own Word doc that we worked on, had to somehow merge them right before it was due.
Yeah. Eventually it has to get down to like one person doing the merging, right? Is that you?
No.
Oh, okay. Good. That was me with one manuscript, so it's really frustrating. Who has a good experience that they want to share? Something that they felt maybe wasn't perfect, but at least worked out nicely. It was a good experience. Yes.
Just in general, I've recently started making GitHub Flow like the default for requirement for doing any collaboration, and it's been great. Issue integration, really great.
Excellent. Cool. Well, that's exactly what we're moving on to is version control. There is a better way than this. For me, it wasn't data files; it was Word documents. But I mean, if I did a search for this WASP genome project, you're going to find probably 6 dozen emails in my inbox that have different attachments, and it's going to look like this. DSS comments, VB comments, final this one, and there's just a better way. So version control systems were designed originally by software engineers for software engineers for basically managing code and collaboration. Kind of the software that's in vogue right now is called Git. It's pretty revolutionary in a lot of ways, but it's also kind of clunky and frustrating in other ways. But one of the really nice benefits of using Git is that there are services out there like code hosting services like GitHub. There's alternatives like Bitbucket and others, but GitHub is definitely the most popular one currently. And what these allow you to do is basically store a history of your code and your data, all the components associated with your project, and then take snapshots, versions over time. And then it provides a platform for you to collaborate with your other contributors, your colleagues in this project. Some of the really nice things that this allows you to do is you can tinker with your software without worrying that you're going to mess something up. Or what a lot of people end up doing is, okay, I have the original directory, I'm just going to copy the directory or copy the file, and then I'm going to work on that copied file. Well, again, what happens when you're done and you have something that you like? How do you merge that back into the original? Or do you just start doing all your work on the copied file or the copied directory? It can quickly be a mess. Version control systems provide a structured environment for you to do exactly this type of thing. You can make changes to your files. You only have one copy of your file at a time. You can store those changes. If you like those, you can merge them in to your original files. If you don't like them, you can discard them. You can go back and see what your file was at any particular point in the past where you've stored a snapshot. Very helpful to be able to work with your code that way. And then, yeah, these code hosting platforms like GitHub or Bitbucket, they allow you to host your code, and then you can have discussions. They provide bug trackers and issue trackers where you can discuss features. You can submit changes to the code, and before those changes are actually integrated, you can evaluate them. Say, hey, can you do a review of this code, please? And others can take a look at it. You can talk about how it's going to affect the behavior. If you have your automated tests going, you can actually execute those on the changes before you integrate them and make sure that everything it's not going to break anything. So yeah, some very cool and very important features. Some other things that might be of interest. We talked about being able to reproduce your work earlier. Version control systems provide a complete provenance of your project history. They also provide transparency in your process and your software project. And after talking with several scientists that don't use version control and the strategies that they use for doing this type of stuff, I would argue that not using version control is a borderline professional, I don't know, malfeasance. I don't know if malfeasance is the right word, but it's a professional obligation for you to be using this. It's very basic and very important. So I have a couple of links down here. They might be too small for you to see, but Kartik Ram 2013 paper on Git and how it can be used in science, and then Blissjack 2016, a quick introduction to version control. These are two papers that are very good for those that want to start using version control for science. Okay, so these are the ideals. This is what we want our software project to look like, what we want it to have. So the question is, how do we reach that point? How do we get there? Traditional software development is actually a pretty planning-intensive engineering discipline. For a long time, developing software required a lot of upfront, writing out really dense technical specifications. This is exactly what it's going to need to do. You need to get managers involved to estimate how much time each particular component is going to take to build, integrate them all together. This type of approach didn't really have a name until the 1990s, when an alternative approach started becoming popular called Agile software development. Now, in academic circles, the engineering approach is kind of referred to as the sturdy approach, as opposed to the Agile approach. Honestly, in practice, there's more similarities than differences between these two. You're kidding me. Okay, I hope that was a fluke. So, just a really quick overview of these. Agile software development is all about rapid iteration. Any requirements that you have for the software are typically informal and or underdeveloped and or constantly changing, so you need to be able to adapt quickly. When you're collaborating on such a project, you have frequent, usually daily, short progress updates, and this type of approach works really well for small teams. Again, this kind of 3x3 approach. A small number of people working for 3 to 6 months on a particular project. The more sturdy engineering type approach is based on the measure twice, cut once principle. You do a lot of more planning up front. You typically have requirements that are more stable, more formally defined, and you have management that actually enforces scheduling, and you predict how much time things are going to take, and you have some expectation that you'll abide by those timelines. And what the benefit of this approach is that it can scale to much larger projects than this kind of more off the cuff approach in Agile. We're going to focus more on rather than delving deep into these two different approaches, what works well for both of these types of strategies. So one of the things that has been proven to improve the quality of code the most is code review. This isn't a surprise to academics review each other's papers. So what about review of code? An analysis several years ago reported that code review in science almost always is going to require knowledge of the specific scientific domain to be useful, and it's more useful during the development of the software than it is when the software is, I guess, quote unquote completed, or when it's submitted to be published. So the idea is that the scientists that had never done code review before, and then they started they got involved in code review felt like it is much better to, as you're implementing the software, to get feedback along the way. One of the challenges is that domain experts in specific areas are scarce, and there's typically not really a whole lot of incentives for this type of review, especially on personal projects like dissertations, theses. So really, at present, this is only reasonable for team projects. Another thing that's been demonstrated to have a really positive impact on software is pair programming. The idea is that you have two programmers working together side by side, doing, I guess, real-time code review. One of the benefits of this is that it helps bring new team members up to speed quickly. Some findings from some empirical studies show that this reduces the amount of distractions from social media or other things that might slow you down. And the idea is that every hour you kind of switch places. One person is the driver doing the actual coding, the other person is the navigator, kind of discussing, providing feedback, and then every hour switch spaces and just do that back and forth. So one of the issues in getting this to work in research software projects is that if your software is working on some very highly specialized problem domains, it can be challenging if the two people that are doing the pairing are kind of have different interests. For example, in our research group, we're working on a software project for, in general, just DNA sequence analysis, but a lot of our group members have different areas of interest and expertise within that broader area. Some of us work on DNA assembly algorithms, some of us work on genome variation, and some of us apply these tools to study gene expression in environmental samples or whatever. And so if you were to put us together to work on some very kind of highly specific research questions, it might not be as useful to get two people looking at the same code. For more general aspects of the code, it might be okay. Mentioned test-driven development briefly earlier. The idea with this is that, again, you have some functionality that you need to implement. And then the idea is to write the test for that functionality before you implement it. Say, I need to make this calculation. So given this input, what should the result be? And calculate that by hand first, and then you write your code to make sure that, okay, the code, when I execute this test, it should give me this result. And then once you have implemented the code to pass the test, then you go back and clean up a little bit and merge that in. So the claim is that doing this type of approach, writing the tests first, helps you to design the software better, and it ensures that you actually get your tests written. Unlike some of these other things like pair programming and code review, empirical studies do not confirm that it actually makes any measurable difference in the quality of the code. But a lot of people that do this approach, they say it's the bee's knees. It's really good. So something to consider. So with this, we're going to take another short break to discuss, kind of get the idea of what test-driven development is. One of the really basic operations in the field of geographic information systems is on a map. If you have certain polygons, to be able to overlay those polygons and then take the intersection of those. And so in the simplest case, we have two rectangles represented as the two corner points, And then you want to be able to determine, okay, the overlap of this rectangle and this rectangle is this rectangle. So imagine for a second that you're writing code in your research software that you have to implement this overlay function to return the overlap. What are the 3 most interesting tests that you would write to make sure that this works correctly? You want to describe this in terms of your inputs, the 2 rectangles that you're getting, and then what you expect the output to be, and why that's important. So you don't have to assume that anything is going to be funky with the input. You're not going to get like Bob as your input. You're going to get 2 rectangles. So anyway, let's take a few minutes, like before, come up with some answers on your own. What do you think would be some effective, interesting tests to write for this? And then after you've done that, talk to your neighbor and then discuss what you think is the best. And then we'll come back together after about 5 minutes or so.
Do you have a list of?
I've got some ideas, but I'm not fishing. No. About another minute or so. If you guys are ready, we can go ahead and discuss now. Okay, so Who wants to volunteer? What's one example of an interesting or helpful test that we could write here for this function to make sure it's working correctly?
It might be the most obvious one, but make sure you don't have like negative output links on the sides.
Yeah.
They're negative, or they're not longer than the inputs. Things that should be physically impossible for overlaying.
Yeah. So if the rectangles don't actually overlap, then negative overlay doesn't make sense. So that's one test that you can do. And then, the one question, this is a kind of a design question, what do you want to return in that case? Do you want to return like the distance of these, or do you just want to return an empty set or a 0 or a none? That's a design consideration you might not make. What else?
It's a geospatial thing, geoshape, and you can just plot it and plot 3 shapes right here and just see
Okay.
the match.
So you're saying plot them and then visualize?
Yeah.
Okay. So yeah, that's, I think especially for writing the test initially, that can be helpful in making sure that behavior works. In terms of automating that, that's the type of thing you actually want to get away from, having to, every time that you run it, to make sure that it works correctly. The idea is to, okay, how can we have the computer check to make sure that this is correct? Yes, please.
We also want to see that they're in the same coordinate system, with the input to the output, so that when we go to the overlay, it corresponds to the same coordinates.
Okay. So are you saying like radial versus Cartesian, or?
Well, like you have the NADBT projection versus the WDS projection.
Okay.
Inputs could be different projections in the coordinate system, and you may think you're putting the same thing, but you get completely wrong results.
I see. You definitely know a lot more about GIS than I do. So you're getting into some details that I hadn't thought of. Yeah, that could be important.
Ensure that if the rectangles simply share an edge, no overlap is affected as well. How do you, is your array inclusive or not?
Yeah, no, I mean, I think, whether you ask an engineer or mathematician, you might get a different opinion whether you should have, if a 1 pixel line, is that a rectangle? Is that a special case of a rectangle, or is that no overlap? I guess that might be a design decision for you to make. But yeah, you definitely want to test for that.
The other limit we can put besides the ones that the area shouldn't be more than the addition of those two areas.
Yes, that's a great test. Awesome. That's one I hadn't thought of.
So one point raised here was that coming up with good tests for this is almost as hard as writing the function in the first place.
Yeah.
But I think that's a feature, not a bug.
Yeah, no, I think that's. I mean, I think that the idea of this approach is that you put in some of that hard thinking before you actually go to write the code. And what the benefit that you can get from that is that you have a much clearer mental model for going in and writing the code. And then when you go to write the code, it's almost like you're not thinking. It's almost mechanical. Like, okay, I know kind of the problem space is fresh in my head, and I just execute the solution. Again, science doesn't necessarily say that this is a better approach, but I haven't studied the literature extensively. I don't know if these are just poorly designed studies that should be detecting an effect or not, or if it's really just wishful thinking. But I certainly have anecdotal evidence from myself that I think this is great. But yeah, so the problems that you encounter in your research might be similar to this, might be different, but this is a powerful approach that you can use to testing in your research software. We mentioned automated testing several times already. So as long as these tests are automated, one common approach is to run continuous integration. The idea is that whenever you have a piece of code or changes to your code that you want to make, that you have a system set up so that as soon as you submit these changes to say, hey, I want to merge these changes into the main code base, the system will say, okay, let me tentatively merge these in, run all the tests, and make sure that you didn't break anything. And so, yeah, this ensures that the baseline state of your code is always runnable. And that, adding new features, extending your code, reorganizing the code, or anything, none of that breaks anything that's already working. So there are several different options for continuous integration. If you have your source code hosted on one of these sites like GitHub or Bitbucket that is free for open source, there are free continuous integration services that will hook up to those. Travis is one in particular. There's others like CircleCI and Drone, just to name a few. These are all very similar in kind of the high-level features and maybe a little different in some of the details. You can also use these services for private projects if you would like to keep your code private until it's published, for example, but to use it privately, that does require a payment plan. Alternatively, you can run CI continuous integration internally. There are free and open source software solutions to help you with this. The only problem is that you have to bring your own hardware, you have to configure your own hardware, and you have to make sure that hardware keeps running, and that can be a headache sometimes. But on the other hand, it gives you more flexibility. You can have longer builds, and so that's an option. We mentioned these services like GitHub or Bitbucket. Ticketing systems, also called bug trackers or issue trackers, are very common in these types of systems. And you can use these to track bugs in your software, features that you want to add, kind of make assignments and make a division of labor, who's working on what. And this is a great place for you to foster some open discussion on the software. And one of the things in our research group that we use it for a lot is just like, okay, if you go through the software and if there's a bunch of changes or a bunch of things that you want or need to do, this is a great place for you to take notes and just describe the problem, get it down there, and then just forget about it. You don't have to think about it anymore. And these technical details that aren't maybe necessarily interesting to the science, you have them recorded somewhere, and so you can really save your brain for thinking about important things, and then have a record of things that you need to go back and, when you have the time, take care of these other things. So it's great for that. Here's a screenshot of the issue tracker for the Genome Tools library, an open source software project I contribute to. Basically just has a list of issues here. Some of these labels, I'm not sure you can read. This red here is, this has been labeled as a bug with the software. Other labels here like, okay, this is a support question. This is somebody that's using the software and they have a question about how it's working. This is an issue opened up by one of the core developers saying, hey, we need to, I want to make this change. We need to enhance the system. Let's have a discussion about it. So you can add labels to your issues and kind of a place for people to come together and discuss the software. Our research group has the KHMR package. Very similar idea here. Different issues labeled and categorized. Not all of them, but some of them. If we click on one of these, some of the issues are just like, okay, here's a note. We've had, this problem. This is something that we need to address sometime. And you can see that this is written back in June. We haven't fixed it yet, but it's there. We know that it's something that we need to do. A lot of our issues look like this. A lot of our issues look like this. Long, drawn-out discussion. Okay, this is the problem that we have. People weigh in with their experience. They weigh in with their opinions. Sometimes the opinions are strong, sometimes they're not, but it's a place where we can discuss the issue. And then, when somebody actually finally submits a fix to this, there's a way for you to refer to different issues and refer to different changes in the code, and it's all integrated to a nice platform. So this is something that's very helpful for the development process. So I think I need to take a couple of minutes to talk about some compromises. This is all great. This is all very important, but there are a lot of things that you could spend your time working on and doing to make your software better at a technical level. And honestly, at the end of the day, as an academic, you're going to be evaluated by your research output as measured by papers, as depending on your level, or you're bringing in grants as well. You're not measured typically on the software that you produce or the quality of that software. So the things that we've been discussing are very helpful in producing better software that's more accurate, that can actually give you some really novel, interesting findings in your area. But there's a lot of things that you could be doing that are honestly just not going to be worth your time, and you have to prioritize your time. There's a concept that I think it kind of originated from the startup culture, talking about technical debt. The idea is that in your code, sometimes there's a dissonance or discrepancy between the conceptual model that is constantly being refined and improved versus the model that's reflected in the code. And sometimes you have to kind of just work with what you have and kind of do duct tape solutions to it as your model improves. The analogy here is that you're taking out debt. Rather than taking the time to clean it up and fix it and make it better right now, you're just going to kind of, go with it until, for some time. So that's kind of the classical definition. I think more generally, the term technical debt really kind of refers to any informed, deliberate, and hopefully temporary suspension of best practices. In startups, this is necessary for you to actually get a product that's going to be profitable. In terms of scientific research projects, this is necessary to get your project off the ground in the lifetime of your grant. I mean, if you take time to do all of these things up front, chances are your funding is going to be out before you have anything scientifically interesting. So you need to really think hard about what are your priorities, and how can you get something that's good enough now. So the problem with technical debt is as you accumulate it in the initial stages of your project, that makes further developments more complicated. And so there comes a time where if you're going to continue to develop and use the software, you have to go back at some point and fix the initial problems that you decided not to address at that point. But the question is when to do this. So, one approach that you should consider is, iterative development. How fast can you build a prototype of your code that'll basically do some minimum scientifically interesting things? In this case, programming languages like Python, R are very well suited for this. The code is easy to write. It's very well designed to kind of have fuzzy requirements about what variables are in the code and what their types are. Generally easy syntax. As opposed to languages like C or C++ or Java, where you have to be very explicit at every level what this code is doing, what types of data it's handling. So after you've built a quick prototype, evaluate the accuracy. You need to have some kind of testing going on to make sure that it's generating results that are accurate and scientifically interesting. If the performance is unsatisfactory, if it's too slow for you, then you might need to do some optimization. But rather than taking a Python script and rewriting the entire thing in C or C++, you might consider profiling the code and measuring empirically what parts of the code are being run the most, and take kind of a more targeted approach to going in and just rewriting maybe one function in a high performance language like C++. And then clean up the code, maybe not perfectly, but do some type of refactoring, clean up, reorganization, and then just kind of iterate over this. Improve your prototype. Again, evaluate the accuracy and improve it over time. And then in terms of these best practices that we've been discussing, we've talked about version control, we've talked about pair programming, we've talked about code review, we've talked about a lot of things. Don't try to go do all of this today and spend the next 2 weeks like doing all of these things and getting it all set up. There's a lot to be said for just, okay, you're aware of some best practices now, try to gradually integrate these into your development approach. Every time that you need to touch a function, to fix it, to implement a new feature, well, check that code. Just that little block of code. Is it clear? Does it need more documentation? Are there any tests to make sure that it's correct? And just focus on that. And then if you do these types of incremental improvements every time you touch the code, you'll be surprised at how quickly these will propagate throughout the entire code base. So I guess the take-home message is compromise on the best practices if you must. But really, you need to be doing version control. That you can start today. And you need to be doing automated testing at some level. I mean, you just have to be doing that. All code is wrong, but code that you have automated tests can be useful. So one kind of compromising approach to the alternative to the test-driven development is something that has been coined stupidity-driven development. And so the idea is that for the scientifically interesting core of your research project, you test that extensively. You write tons and tons of tests, considering all the different ways that your code can go wrong, and have these automated. And then for the other parts of your code, like reading files into memory or your command line interface or other kind of like boring parts of the code, don't worry too much about writing tests for that. If you find a bug or if somebody reports a bug, okay, I need to fix this bug. I'll write a test for that bug. And then once that's done, just go back to doing more interesting stuff. So I think that's a good compromise on kind of prioritizing and focusing on what's most important. And the idea here is that you're avoiding wasting time writing tests for bugs that just aren't going to appear in practice. So to summarize, we talked a little bit about project organization and software usability. I think it's critical that you implement automated tests and use version control as soon as you can in your research software project. And then as you're able, integrating some tools and strategies like code review, like continuous integration, these things can have a positive impact on your research software project. And don't be afraid to make deliberate compromises, but this is not an excuse to ignore all of the best practices that are out there. Just make sure that you know why you're doing it and have a plan. So with that, go forth and do great things with your research. So that's it. I don't know if you have any questions, but if you do, I'll be happy to discuss anything, or I could, if you have. Yeah.
Yes, so kind of what options do we have in terms of like probably does UC Davis has Bitbucket or GitHub already paid for so that big teams can?
So, go ahead.
I was going to say, GitHub has a notification plan that you can request access and then you have project repository.
Okay.
I don't think UC Davis has an enterprise account.
It doesn't have an enterprise account. There is an organization that you can join, but there's no benefits.
Yeah.
That's what you get in this.
Yeah. So like an enterprise account basically gives you unlimited like private repositories. But yeah, like Louise said, if you have an education email, then you can get an education account where you can have a small number of private repositories. And the idea being that, you know, while you're developing the project, you can kind of keep it private. And then once you publish it, then you can kind of flip the switch and make it public.
Yeah, because the benefit of having GitHub is that everyone uses GitHub, so you get more contributors or integrate.
Yeah.
So I should mention if you're interested, we'll be running, I'll be running some training sessions later this year on Git and GitHub. You want to get some practical hands-on experience with that. And I should say that our lab uses all of these things, so if you just want to come by and check out what we do and how we do it, then we're always happy to talk about it.
Well, if you have any questions that you want to talk about personally, I'll be here for a few more minutes. So thanks for coming.